Welcome back, everyone. In this video, we're going to continue our discussion of work by looking at the mathematical definition of work as a dot product. So what we're trying to figure out is how can we calculate work using a dot product. So this is going to be a little bit different from what we did last time. But the important thing to remember is that work is a scalar resulting from the multiplication of two vectors. Now, we weren't very clear about this, but it's actually force as a vector and displacement. Now, I said distance a lot in the last video, and that's because displacement takes too long to say, but really that's what it is. Work comes from force and displacement. And work is the dot product of these two vectors. So the way that we write this is work equals F dot R. This is the dot product representation, where F and R are vectors. Now they're in bold, but I like to draw the arrows just to be clear. Now this is the magnitude and angle representation, and in this case F really is meant to be the magnitude of F, and R is really equal to the magnitude of the vector R. And the cosine of the angle is the angle between the two vectors, so F and R. Okay, so you have to put the two vectors together to get that angle. The final way that we can calculate work is if we know components, we simply apply the definition of dot product by multiplying the x components and then adding the multiple of the product of the y components and then the z components. And this is good if we're given force and displacement as unit vectors. So just to recap really what dot product is telling us, the dot or scalar product is one way to multiply two vectors together, and it gives us a scalar as an answer. Later on in the course, we'll be talking about the cross product, which is where you multiply two vectors and get out another vector. So here are three applications of the dot product: work, power, and magnetic flux. So we're focusing on this first one. And also, remember that these are biggest when the vectors are completely aligned and there's a zero angle. So in other words, we said previously that the dot product, way back in the vector review videos, but that we said that the dot product is the projection of one vector onto another. So work is the projection of F onto R, or vice versa. And of course, you get the biggest value when they are parallel, so that the projection is basically the same. So why is work a dot product? Well, this is what we're talking about. Work is F dot R, which is FR cosine theta, and only the component of force aligned with this displacement does work. And if you think about it, what is the component of F that's parallel to R? Well, it's F cosine theta. So therefore, F cosine theta times R. Okay, so let's do some examples. First example, vector A is a magnitude of 8, B is a magnitude of 12. They make a 40-degree angle. We want to find the dot product. So definition of the dot product is magnitude of A times the magnitude of B times the cosine of the angle between them. Well, this is one definition anyways. Okay, so 8 and 12 and the cosine of 40. Work that all out and you get 73.5. Okay, so that is A dot B. Okay, it turns two vectors somehow into a scalar, and that will have some sort of unit that's attached to it. Okay, next example. We have a force that acts on an object that undergoes a displacement. How much work was done on the object by the force? Okay, well, we know that work is equal to F dot r, which is equal to fx rx plus fy ry plus fz rz. So again, this definition of work is useful when we are given components. Okay, so that's 5 times 4 plus 6 times -9 plus -2 times 3, which if we work that all out is equal to -40. And if we're careful about this, all of these numbers are newtons and all of these numbers are meters. So we get Newton meters, which is the unit of work, which we can also call joules. Okay, so 1 joule is defined as 1 Newton times 1 meter. Okay, now one way to think about this is to actually draw it out and to look at these vectors. All right, and so if we have x going this way and y going this way and z going that way, we could say that f is approximately this direction-ish, and we can say that r is kind of sort of in, well, that's bad, kind of sort of in this direction. If you think about it, positive x for both of them, but a positive y for f, a negative y for r, and then f has a negative z and r has a positive z. Okay, so we can kind of think about how this would look. And so let's do one more example. We're given a force and a displacement that in this case are just two-dimensional, and we want to know how much work is performed and what the angle is between the vectors. Okay, so when you have components, you just multiply and add. So 5 times 2 plus -3 times -1. So that's 13 joules, because we have newtons and meters. What's the angle? Well, work is also defined as the magnitude of F times the magnitude of D times the cosine of the angle between them. So the magnitude of F is square root of 5 squared plus 3 squared, which is going to be root 34, 25 and 9. Magnitude of D is going to be root 4 plus 1, so root 5, right? 2 squared and -1 squared. So that means that work, which was 13, right? So work is 13, is equal to the magnitude of F, so root 34, times the magnitude of D times the cosine of the angle between them. Okay, now if you work this out, you get that this angle is about 4.4 degrees, which seems kind of crazy, but then if you actually draw out what's happening, okay, so here is x and y, just a 2D picture. So F is 1, 2, 3, 4, 5, 1, 2, 3, okay, there's F, and R is 1, 2, and -1. So F and R are almost parallel, but not quite, so that means that the angle between them should be very small. Okay, so next time we're going to look at what happens when you have forces that are not constant.